These notes are going to be looking at the role of charge in chemistry. We will be looking at how substances get charged and what happens once they become charged. So we have the macro scale and the micro scale. So looking at charge on the macro scale, we see that opposite charges attract and similar charges repel. This is pretty similar to what we've seen before, especially if you play with a couple of magnets and you have them going one way, they attract each other, and if you flip one of the magnets over, they'll be pushing back away. Kind of the unknown is what's going to happen to neutral objects, and we find that neutral objects are attracted to anything with a charge. So if something has a positive or a negative charge, it doesn't matter. A piece of foil will be attracted to it. But they exert no force on other neutral objects. So they'll just kind of hang loosely if they're around any other neutral objects. So here we're going to talk about the microscale, what is going on with those particles and what happens with charge. Now, when we look at the particles, we see that they have both a positive and a negative charge normally. These will cancel each other out, so we're left with neutral. These objects, these atoms, these particles can be charged if the positive or negative become unbalanced, or there's more positive or more negative. So either the positive or the negative charges were transferred, and the big question is, which is transferred? So to figure out what pieces are removed or transferred, we go to J.J. Thomson. And J.J. Thomson used a cathode ray tube, which is similar to if you have old tube TVs. This is essentially what was going on. So he got the transferred piece is this one right here, and he put this in the cathode ray, and he watched it would come across the cathode ray, and it would light up somewhere along this plate down towards this side. To determine if this piece was positive or negative, he put charges and charged these little plates. So this plate down here is positive and this plate up here is negative. So if this little piece is negative, then it'll go towards the bottom and it'll be attracted towards the positive side. If this little atom or this movable piece is positive, it would be attracted towards the negative plate and it would hit probably up here. So again, if it was negative, it would be attracted to the positive and it'd hit towards the bottom, and if it was positive, it'd be attracted to the negative and it would hit up here. Thomson thought that it was a positive piece, so he was expecting a lot of hits and a lot of pings on this side. Well, what we see is when he let it go, it would come down, and it kept over and over and over again, kept hitting down here towards the bottom. So to rule out that it was gravity that was pulling that little piece down towards the bottom and not the positive plate, he switched the plates, and he now put the positive up at the top. So if this was really negative, as our last experiment showed, then we would see it hitting up towards the top. If it were still being affected by gravity, we would see it hitting down at the bottom. And of course, when we saw this little movable piece of the atom was able to curve up and hit the top of the screen because it was charged and with a negative charge, and it was attracted to that positive. So what does that mean for J.J. Thomson? Well, all of his experiments in the 1890s showed us that charges were able to be transferred, and then it was those negative charges that were moving around. But we still need to kind of decide what is positive, and at this point we don't know that there's a nucleus and all those little pieces. So we had this kind of goo idea. So you have like this big piece and you have these negative little charges inside. Well, all of this area out here, all of this is going to be our positive, and then you have these little pieces that are negative. So all of these little negative pieces throughout. All right, so now Thomson has this idea, and he's got to spread this idea, and he's got to come up with a way to explain it to all of the simpletons that weren't quite science-minded, and he had to come up with a way that it was easy. So he thought about this plum pudding model. So to kind of explain plum pudding a little bit, it is kind of like a really heavy cake, like a bread almost, that has these dried plums in it. So you can kind of think of it like a really thick blueberry muffin, or since you know, we do still have like fruit cake, so it'd be like that gross cake with dried bits of fruit in it. So he said that the positive core was the dough. Okay, so that was kind of the bread or the pudding area of it. And then the negative pieces were the plums. So these big chunks of fruit were the negative charges that could be moved all around. We don't really know much about plum pudding. Most of you probably haven't tasted it, but we have had chocolate chip cookies, and I like using this model a little bit better. It's a little yummier. So we have these scoops of dough are going to represent our positives core. So you have like this atom. The cookie is this atom, and you have the dough is positive. And then you have these little negative charges. The chocolate chips are stuck inside. Okay, so expanding this and kind of talking about some facts that we have with this chocolate chip cookie and our atom. So we see that chocolate chip cookies can be removed from the dough. Well, if we take these negative chocolate chips out of the cookie becomes positive. That's what happens with our atoms. If we take these negative electrons out, the positive cookie just gets more and more positive. So we don't have that balance from those negative charges. Some dough can attract more chocolate chips. Okay, so you might have one cookie that has a ton of chocolate chips into it. Well, that would be a negative cookie, right? Same thing happens with the atoms. Some of our atoms want more electrons than they already have. So these atoms will grab extra electrons and become negative. Okay? Chocolate chips can move around inside the dough. So you could get a cookie with all of the chocolate chips towards the middle or towards one side. Same thing happens with atoms. We can see that by placing charges closer to or further away, we can influence where those electrons are going to hang out inside that atom and give us a slightly positive or a slightly negative side to our atom. And then chocolate chips are repelled by other chocolate chips. This is similar to our macro scale where we said positive or similar charges repel each other. Same thing with our electrons. Two negative electrons are not going to want to be next to each other because they're both negative. All right, in a normal situation, our dough would have the exact number of chocolate chips to make it balanced. So if we're going to look at atoms, we would have hydrogen has one electron. Well, to be balanced, it has to have one positive charge in it. So those balance each other out. Same thing for carbon. It has 6 electrons, so it has 6 positive pieces to balance it out. Sometimes our dough can lose these electrons, and then it becomes positive. And then sometimes our atoms can gain chips or gain electrons, and then it becomes negative. This is a really great simulation on what is going on with the electrons and the charges. It's called Balloons and Sweaters. If you just type into Google PhET simulation, I believe this one does have to be done on a computer, but it really will let you manipulate the charges between a balloon and a sweater. So knowing the charges of the atoms is great, but sometimes it's better to understand what is going on with those atoms inside a whole substance. So We're going to look at foil and paper. And foil and paper have interactions with charged things because even if they're neutral, they're going to have an attraction to anything that is charged. The foil tends to react stronger than our paper does, and we want to kind of understand this difference. So one thing we noticed that in neutral objects that are just sitting there, the charge is evenly distributed amongst the whole object. So foil is a conductor. It allows its negative charges to move from one positive core to another. So if you have these atoms all lined up and they all have their electrons that are supposed to be stuck to each one, if you are a foil or if you are a conductor, we say that these are delocalized. They're not stuck in one place and they're allowed to jump. So if we look at this drawing down here at the bottom, each of these little electrons were able to skip over and miss and leave their atom to get closer to this positive charge that they want to be. When we have an insulator, something like, for example, the paper, we see that their cores hold on to those charges a little bit tighter. So the electrons are allowed to get close to this positive charge, but they line up in the atom, but they're still stuck there. So the way I kind of like to think about this is the conductors are like those wild, loosey-goosey parents who allow their kids just to go wherever they want, or for the atoms, their electrons, to go wherever. Whereas the insulators, those atoms are like the really strict parents who are like, no, you can't go over there, you have to stay here, you can look out the window and see the kids playing, but you can't go and play with them. So we say that that these are kind of stuck. They're like a localized charge. We see that this term polarization, so in the conductors, the polarization is really strong and it allows those electrons to move, whereas here it's really kind of less pronounced. Really, we see these two things really fit well with our periodic table and our metals and our non-metals. So on the left side of your periodic table, and you'll see kind of a little stair step drawn in there, that the left side are our metals, and these are the positive cores that don't really hold on to their electrons, and they tend to allow them to kind of go and move all over the place. Whereas our non-metals, or the ones to the right side of that stair step, if you're looking at the one in the classroom, it's the big white area. Those hold on to their electrons a little tighter or even pull more electrons towards them. So if you would please label your periodic tables with the left side being metals and the right side being the non-metals. Generally speaking, we're going to have more positives, or we're going to have the metals are going to tend to lose those electrons because they are kind of free to move all over the place, and our non-metals are going to be ones that gain. They kind of want to hold on to their electrons. So the metals, since they give electrons, they will be positive, and since our non-metals kind of take the electrons, those will be our negatives. Here is just a really good slide that kind of summarizes everything. So we have our conductors allow these electrons to jump so that they can get close to the positive charge, whereas our non-conductors kind of just allow them to get close, but they can't go all the way over. Like we see the conductors, and really this is good because we want electricity to go through our metal wires, but we don't want them to go through the rubber coating on the wire. So we can use this conductor, non-conductor to help move these electrons exactly where we want them to go.